Yes, welcome to this dissertation of Hiba Alqaysi. I'm Professor Mattias I've been the supervisor for Hiba during her PhD studies, together with Dr. Najim Lawal. In this procedure, we have an opponent that will examine this work, Professor Fabio Poiesi from Bruno Kessler Foundation in Italy. Welcome, Bruno. And the other part in this is the grading committee that is composed of 3 persons. We have Professor Bernhard Rinner from University of Kagenfurt in Austria. Welcome. And we have Professor Haibo from the Royal Institute of Technology in Stockholm. And we have an internal member, Associate Professor Göran Thungström, here from Mid-Sweden University. We have one reserve also, so Professor Henrik Andersson, that we probably will not need in this procedure. So, the procedure for the dissertation is as follows, that the Hiba will start by presenting her work, summarizing it, and then we will have a short break, 10 minutes, for ending the broadcast on YouTube and removing the gear for that. Then the floor is open for the opponent to discuss the thesis together with the respondent, Hiba. When this is finished, we move on to the grading committee that will continue the questioning one by one. And the final part is that the audience in the room and on the audience on Zoom will be able to ask questions at the end. When there is no more questions, we will pause this session in Zoom and move on into another session. That's me, the supervisor, the opponent, and the grading committee, to have a discussion, and the grading committee will decide on the grade, pass or non-pass, for the thesis. And we'll resume here in this Zoom room to announce the result. So this is the procedure. We will then move on to Hiba, if you have anything to add to your thesis, or if you present it as it is.
No, as it
Good.
is.
Then you can start your presentation.
Okay, thank you, Mattias. Good morning, everyone. My name is Hiba Alqaysi, and today I will be presenting my doctoral thesis titled Cost Optimization of Volumetric Surveillance in Sky Monitoring towards Flying Object Detection and Positioning. In sky surveillance, open large volumes are required to be monitored, like wind farms, airport runways, and border surveillance. In wind farms, for example, birds collide with windmills, which result in habitat loss and change in migration routes. This contradicts with the main profile of wind farms, which is being environmental friendly. Similar problem of sky monitoring in airport runways, where visual surveillance is necessary in addition to radar monitoring systems. Available sky surveillance systems implementation may include, for example, fisheye cameras that are complicated to calibrate as compared to the standard perspective camera. The lens causes distortion in the image, which leads to more post-processing afterwards. Also, one camera deployed does not give enough resolution of the scene. The radar systems do not provide visual information. of the scene, as according to wind farm operators, data from these systems are not enough for surveillance. Therefore, the standard camera represents a better option for implementing sky surveillance. Monitoring a volume is different from area surveillance because of having a 3D target space and flying objects within it rather than having them confined to the ground. Therefore, it's mostly inapplicable to utilize 2D surveillance approaches to volumetric surveillance. This brings challenges in designing and deploying volumetric surveillance systems, including the camera placement, coverage, configuring its design and cost, and the system ability to detect and position flying objects. Which leads to the following research questions that are addressed in the highlighted papers. First, how can the multi-camera dome be placed to provide full coverage of a volume? How to configure and construct a cost-efficient multi-camera dome, and how to accurately detect flying objects within the volume. The multi-camera dome composes of a number of cameras integrated into one node that are not necessarily all of the same type. These cameras are arranged such that a hemisphere around the dome center is monitored. And the multi-camera dome is introduced in the literature as an efficient implementation of volumetric surveillance as compared to the implementation of grid of multiple cameras. The combined field of views of the cameras in the dome form a hemisphere whose base on the ground is a circle. That's why utilizing the thinnest covering of circles in a Euclidean plane results in placing the dome in a hexagonal pattern to fully cover a plane. However, the volume above a specific monitoring height should be fully covered to detect the objects within the volume. Therefore, monitoring constraints should be defined and considered. The constraints defined for are the flying altitude that full coverage should be achieved below it, and the minimum detection pixel resolution at distance r, which is the dome coverage radius. In the figure here, the dotted arch represents the coverage of the dome when at the defined flying altitude A. In the thinnest hexagonal placement, every three adjacent non-collinear domes form an equilateral triangle. Its side represents the distance between the dome's centers. This placement provides full coverage on the plane, on the ground level. However, in a 3D, intersection points will have zero coverage when the objects fly over them. Therefore, the distance between the dome centers should be adjusted. As we calculated here as S prime, while maintaining the thinnest hexagonal placement. In order to measure the effectiveness of a specific node placement, a method to evaluate the detection position percentage of placement based on different pixel resolution constraints is developed. The defined criteria were measured using tracks of flying birds that were captured here in the figure, that were captured using GPS data loggers as latitude, longitude coordinates in 9 square meters. For example, the figure here shows a trace of flying bird that was used in the evaluation, and the trace has multiple samples that represent the bird's location at different times. Multiple configurations were tested using the hexagonal placement and the evaluation method. For example, configuration 1 it has the dome radius of 1 kilometer and a minimum pixel resolution for detection as 3 pixels per meter, and the area that was required to cover was 9 square meters. For that configuration, 7 domes should be deployed to ensure full coverage when the flying altitude is assumed to be 200 meters. For that placement, the defined criteria were calculated for the 6 captured trajectories of flying birds when the flying altitude was assumed to be 200 meters and 100 meters. Detection at both heights was 100% and of the 6 tracks, and we can see that we have higher positioning percentage and pixel resolution for all the tracks when the flying altitude is lower. Next, I'll present the design exploration method used in this research for the multi-camera dome that addresses research question 2. Because each camera has a discrete field of view, the number of cameras are arranged to monitor a hemisphere. Therefore, it's assumed that these cameras are arranged into multiple layers, as shown in the figures. And the figures here with domes of 2, 3, and 4 layers. The vertical field of views of all the layers combined should cover a minimum of 90 degrees, and the horizontal field of views in one layer should cover a minimum of 360 degrees. The cameras are identical in the same layer and may differ from the ones in the other layers. For the design constraints, the following set were defined. The maximum number of cameras in the node, the coverage radius of the node, that is the distance from the dome node center, and the minimum pixel resolution required to detect an object at that distance. And the latter 2 constraints can be used to define the dome capacity, and that is the multiplication of the 2. Sensor and lens pairs that satisfy the monitoring constraints of pixel resolution and the coverage radius are used to compose the solution space S. Each solution has the following properties: the total vertical angle covered by all the layers, the number of cameras, and the cost of the solution. The design exploration method estimates the cost of each member of the solution space and select the one with the minimum cost as an optimal. The list of cameras and lenses that was used in the design exploration is shown here, and the prices in these lists were sampled in 2016. In the table here, we have design exploration of 3 layers multi-camera dome. The design is constrained to a maximum number of 40 cameras, and the node capacity ranges between 5,000 to 9,000 pixels. We can see that larger node capacity generate more costly solutions, but a higher number of cameras in some cases can generate lower node costs, such as here, where we have 20 cameras cost less than 19 cameras in a node. The table also shows that it is not possible to implement 9,000 pixels capacity dome with less than 40 cameras arranged in 3 layers from the available set of sensors and lenses. So placing the domes in a hexagonal pattern fully cover a volume while maintaining overlap coverage between adjacent domes. However, volumes above the monitoring height are basically not required to be covered, as shown here as an overhead coverage. And so is the overlapping volumes. So when the constraints of the monitoring height and pixel resolution are considered in the node design, then the required volume, the actual required volume to be monitored for each node placed in this pattern can be modeled as a hexagonal cylinder instead of a hemisphere. For that design, cameras covering non-overlapping volumes should have a minimum coverage range up to the monitoring height, and the coverage range of overlapping volumes then should be bounded by the cylinder radius. The dome is then divided into multiple layers, and each of them has its own coverage radius that satisfies the monitoring constraints as defined here. A stacking number of cameras at the top layer of the dome causes multiple overlap in that layer, which is an extra overhead in coverage and number of cameras. And to overcome that, only one camera with wide angle of view and shorter focal length can be mounted on the top layer. In this case, the top layer forms half a layer when the layers are arranged vertically from the bottom up to cover 90 degrees. When both the hemispherical and cylindrical designs are placed in the hexagonal placement pattern, and in the cases when pixel resolution constraint is met at bigger distance than the dome radius, like we can see here in the figure, then the cylindrical dome has a higher placement radius, and this placement radius fulfills the coverage constraint at specific height, while the hemispherical dome placement radius should always be fixed in order to maintain full coverage, even if the placement radius is higher than the defined radius, in order to ensure full coverage requirement at the flying altitude h. This maximizes the coverage of the cylindrical dome as it covers more square meters per dollar, and consequently number of domes required to be deployed is reduced, and so is the total cost of the system. In this table, we can see a comparison of node cost in dollar and the placement radius that satisfies the pixel resolution requirement for the two designs. The cost of the cylindrical dome is optimized as compared to the hemispherical dome. It is cheaper per node at all tested heights when the number of layers are 2.5 and 3, whereas when the nodes are of 1.5 and 2 layers, the hemispherical design is cheaper. However, it has a smaller coverage radius as compared to the cylindrical design. Next, I will talk about object detection in volumetric surveillance, which addresses research question 3. specifically in-flight object detection in wind farms. For this problem, number of challenges arise, like lack of public data sets, having small objects that change in size, distance to camera, orientation, in addition to background changes and illumination changes. So then two data sets were collected at two different locations by Mid-Sweden University for this task, and they were manually annotated. Dataset 1 has a relatively static background, as we can see here in the figure, in terms of moving clouds and illumination. And dataset 2 has more dynamic background and variant illumination. And this dataset was used for training. Object sizes in both datasets are considered small, as they occupy a very small percentage of the image frame. In order to optimize this object detection task, we explored how a traditional computer vision algorithm performs against deep neural networks. The traditional detection algorithm of background subtraction achieved good results when was tested using dataset 1. The precision, and recall were 84 and 60% respectively. The figure here shows is an example of a frame from dataset 1 with one correctly detected object. However, this method performed poorly when dataset 2 was tested due to illumination and background changing. Shown in these two figures, here's a frame where the frames are from dataset 2. Here's the frame with the ground truth of 5 objects, and the background subtraction predicted 174 objects, which is extremely off. So in order to overcome that problem, deep learning based detection was used. And when objects are less than 10% of the image, then YOLO performs better than other one-stage detectors. Also, at the time of doing this research, the most recent iteration of YOLO was version 4. Therefore, 3 YOLO v4 based models were used for flying object detection. Model 1 is a standard YOLO v4 detector that was trained using full 4K frames from dataset 2. This model had a high rate of false negative, especially for small objects. And to address that, Model 2 splits the input frame into 4 frames before feeding them into the network. And it was trained also using dataset 2. And it detected small objects better than Model 1. However, frames in the acquired datasets are extracted from video sequences, which means that temporal information from successive frames are connected. And so incorporating temporal features of object makes the network learn the object better, since it appears in successive frames, and consequently it improves the model accuracy. So Model 3 uses temporal information such that instead of having 3 RGB channels store the values of the pixel values of the objects, then we have the R channel stores the pixel information of the previous frame, and the B channel will store the information from the the next frames at time t+1. The frames are then tiled into 4 tiles and fed to the YOLO network. Model 3 outperformed both the standard YOLO in Model 1 and the background subtraction for detecting small flying birds in 4K frames. In this table here is the testing result of the 3 methods using both data sets. And although Model 3 was never trained using the Skagen dataset, it still achieved very good testing result of 92%. Also, in these 2 figures, we can see that majority of objects in the testing datasets from both datasets were correctly detected. For example, here, out of 156 objects in the smallest category of objects between 30 to 200 pixels, 145 objects were correctly detected. In summary, the presented research answered the 3 main research questions by optimizing the dome placement in a volume using hexagonal placement. The method reduces the number of implemented nodes while achieving full coverage as specified at the specified flying altitude. And the placement was evaluated using the method developed in paper 1. Also using the design exploration method to construct the multi-camera dome and modeling its coverage as a cylinder, the node cost is reduced and the coverage was maximized as compared to the hemispherical dome. Last, for detecting small flying objects in sky monitoring, using CNN-based models that incorporate temporal information of the objects improves inference accuracy. In conclusion, the main contributions of the presented research were to cost optimize volumetric surveillance in order to enable sky monitoring, and that included using the design exploration method and the inclusion of monitoring constraint, which results in constructing a cost-efficient multi-camera dome, and also incorporating temporal features with the use of deep learning improves object detection accuracy and robustness. As a continuation, future work, it would be using the deep learning-based detection model to obtain object trajectories where track points can be back projected into the world. And if they are visible in 2 cameras, then the object position can be extracted in 3D. That concluded my presentation. Thank you all for listening.
Thank you, Hiba.
Thanks.
Then we will have a pause for 10 minutes. So we'll be back at 20 to 10. Resuming with the discussion of the thesis together with the opponent. So see you back in 10 minutes.